So this will be problem number 5, part A from the 2013 AP Calc AB exam. It's a no calculator question, and they give us this graph, and they tell us that f of x is defined by this parabola, and that g of x is defined to be this cosine function. R is the region between the graphs of f and g. That's what we are given the graph of, and in part A we're asked to find the area of R. So what I'm going to do here real fast is just kind of shrink this to give myself a little bit more space to do part A. We're going to need this graph, so we're going to come up and do some doodling on the graph, but there's quite a bit of work, so I just want to get myself enough space here in order to take care of all that work. Now, if we want to find the area of R, R is obviously not a circle, an ellipse, a square, a rectangle, a triangle. It's not something that we would have an area formula for from out of geometry. And anytime you're looking for an area that's in the coordinate plane like this, the process that we've been using is 3 steps. We slice the region, we approximate, in this case, the area of one slice, and then we integrate to add together a bunch of those slices' areas. And so with this slice right here, if I draw it down below the graph, we would want to say, well, this slice is approximately a rectangle, so its area would be approximately the width times the height, and we want to try to figure out what the dimensions of the width and height of this slice would be. So the width of the rectangle is some tiny difference in x values. It's this small dimension from out of the coordinate plane, and what we're going to call that dimension is we're going to call it delta x. So the width of our rectangle is going to be delta x. Now the height of this rectangle is going to be given by a difference in y values, and we want to specify that difference so that it's positive. So we're going to take the bigger y value, and if you notice, the bigger y value is always on this top graph, and the top graph is going to be the cosine function. So the bigger y value is g of x, and then this parabola that opens upward is going to give you the bottom of every slice. So the bottom y value is going to be given by f of x. So we're going to take the area of a slice being g of x minus f of x for the height. I should have labeled that dimension over here, but then times the width of the slice, which is delta x. So the area of one slice can be found by evaluating this expression. I'm going to simplify this a little bit, clean it up a little. Let's see, 4 cosine of 1/4 pi x is g of x, and then minus f of x. Well, I could subtract this quantity right here that represents f of x, but what I'm going to do is I'm going to distribute the negative into everything as I'm writing this down. So minus 2x squared plus 6x, and then minus 4, and then times delta x will get us the area of one slice. We want to find the area of the region, meaning we're going to have to put a bunch of slices into this region, like the one that we just analyzed, and we're going to have to add together all of their areas. We're going to let the definite integral add together an infinite number of those areas for us by integrating this expression. So when we toss this expression into the integral, everything's just going in as is to start, and the one thing that's going to change is at the end of this, when you get ready to copy down your delta x, it's going to change to a dx, basically telling you what variable to integrate this with respect to when it's tossed into the integral. And then the limits of integration here have to be all x values that slices range between. So our slices that we could have drawn are going to range between this point here and this point here, and those x values would be 0 and 2. They've actually provided us with both of those. So 0 and 2. Now it does say to find this area, so we've got a bit of work left to do. We're going to use the first part of the fundamental theorem of calculus, find an antiderivative of this expression, which is going to take a little bit of time. We're going to put in these limits of integration. We're going to take a difference. So hopefully you understand the setup, and now it's just going to all be procedural stuff. I'm actually going to pause the video and work out the next few steps, and then we'll restart and talk about them together. Okay, so now that everything's in place here, we'll kind of talk about the antiderivative and some of the things that were necessary in getting your final result. So we set this up a few minutes ago, and then I recognize that with this piece of the integrand, I have this inner function here, and I'm probably going to have to do a u substitution to evaluate the antiderivative of 4 cosine of 1/4 pi x. So I broke this into two separate halves. I broke it into the integral from 0 to 2 of just the piece that seems like it's going to need a u substitution applied to it, and then plus the definite integral of the second piece, so the minus 2x squared plus 6x minus 4. The work right here, I think you're going to think is pretty standard, right? Antiderivative of that, power rule, another power rule, another power rule. Put in the 2 to that antiderivative, put in 0 to that antiderivative, evaluate and take your difference, and you end up with negative 4/3 for the value of this integral right here. Now, the integral to the left here does require a u substitution, and I wanted to let u equal the inner function, what's inside this set of parentheses. So I let u equal the inner function. I replaced what's inside the cosine function with u. I had to figure out what I was going to replace this dx right here with. And so I computed the derivative of u with respect to x, and the derivative of a number times x is just going to be that number. And then I took a second to solve this for dx. What am I putting in place of dx? Well, multiply the right side of this equation by dx, and then divide by pi and multiply by 4, and 4 over pi du is going to go in place of the dx, so that's what I have here. The one thing that I did not do here is I did not change my limits of integration from x values to u values. If you are going to do that notationally, what you should do is you should make sure that you denote that these numbers, the 0 and the 2, these limits of integration, they're definitely values of x and not u. So that's why you don't see the little note that these are x values here, because it's assumed to be that these numbers are values of whatever the differential is. But since these are values of x and my differential is now a du, I just kind of noted that. I took the antiderivative of sine of u, or of cosine of u, and I got sine of u. I did 4 times 4 over pi, got a constant of 16 over pi. I had to back substitute before putting anything in place of u, since I didn't change these to u values. So I put 1/4 pi x back in place of u. I finally put 2 in place of x. I put 0 in place of x. 1/4 times pi times 2 is 2 pi over 4, or pi over 2. Sine of pi over 2 is 1. Sine of 0 is 0. So we get 1 minus 0 in this set of parentheses here, times this constant, and we get 16 over pi. So the sum, 16 over pi plus negative 4/3, is going to be the area of R. So 16 over pi minus 4/3. If you want to tack on square units there, you can, but it's not really required. Do parts C and D in separate videos.